This is what your diagram should look like. Silver electrode, silver ion on the left, so you can do this half reaction, the reduction of silver ion, 0.80 volts positive. On the right, we have aluminum metal, which can be oxidized, producing 1.66 volts positive. In the solution, you need some ions. The safest thing to do is to have this ions match. So this chloride could be other things, as aluminum could be other things, but this is a reasonable choice. What this means is that electrons come out of the aluminum and they travel toward the silver through this wire. When they get to this side, reduction occurs. So you have to imagine this silver ion actually swimming till it contacts the electrode, where the electron from the aluminum all the way around has arrived to initiate reduction. I'm going to try to do this as a motion picture. The silver ion moves, which means it's no longer a silver ion. It's picked up this electron, and as it did so, it became solid silver right here on the surface of this electrode. That's what this half reaction says. The aqueous ion becomes a solid neutral. Let's write the word neutral metal. So we're creating silver metal at this electrode. On the right hand electrode, it's the opposite. We start with solid aluminum, but it turns into an ion. The electrons go up. Maybe we'll show some electrons going up, leaving this aluminum. Now it comes off the electrode and becomes another ion. That'll mean that you get this electrode is deteriorating. So I'll draw some spots where it might look like it's actually deteriorating. You should see there's a problem on both sides, and that problem stems from the rule that for every plus there is a minus. On the left we have one plus and now two minuses, two negative ions, because one of the positives turned into a neutral metal. On the right it's the opposite problem. We now have two aluminum ions, not enough negatives to go with them. The solution to this problem is to allow ions to migrate from beaker to beaker. That's done using a tube called a salt bridge. So I'm drawing a salt bridge here. I can show you what this looks like in real life in just a second. The ones you'll use in the lab are made of glass, and they're filled with a solution. They're not filled with air. Ions can't fly, they have to swim. So this is H2O plus dissolved salt. The type of salt can be almost anything, and that fills the bridge completely. I'm hoping you now see that on this right side, if there are too many positives, they can emigrate. They can swim where they are wanted, and they can find partners from the other side. So here's the negative nitrate, unwanted, lost its partner. What'll I do? I'll find another one prettier than you. So within the salt bridge there will be positive and negative ions. I won't specify what they are, but they can also migrate to help. So the negative ions will migrate in this direction where they are wanted. The positive ions will migrate in this direction where they are wanted or needed. So you have this ion migration through the salt bridge, which allows you to even out the charges so that there will be an equal number of positives and negatives on the left hand side, an equal number of positive negatives on the right hand side. This is essential for the operation of the battery. If you haven't already done so, please label the salt bridge like so. Here's a salt bridge. It's glass. It's filled with a solution of salt. It has these cottons on the end. Ions can easily migrate through the fibers of cotton, so this is not a barrier. It simply keeps the liquid from falling out when I turn it upside down. The salt bridge is used to span two beakers. One side for the oxidation half reaction, one side for the reduction. And you can imagine, I hope, that ions can migrate through the cotton, through the tube. They can get to the other side. Positives go one direction, negatives go another.